last lecture we have started unit number 3. Okay, will not take much more time. We will start the expression of bending stress. Okay, or it is also called as a bending equation. Guys, remember in your syllabus you have given the only numericals. You have to solve the numericals. Okay, question will be asked on the numerical. So I will skip this derivation part and you have to remember the bending equation. Okay, how to get that bending equation I will explain. Okay, see here we are considered one body. Okay, from that body we will consider the small part. Okay, I have taken two sections, AB and CD section, and we will consider the small part from that body at a distance dx. Okay, a distance dx, and we will consider the one neutral layer from that body is EF. Okay, we are not solving the whole equation. That's why we are consider the only small part from that body, and when you integrate that small part, then you will get the whole equation from that body. Okay, before loading, see what happened. Before loading, we are not acting any type of the load on that given body, then body will get as it is. But what happened when you apply the some load, okay, point load or MDL or MVL on that body, then this body will be bent. This body will bend. Okay, then see the figure number 2. After loading, we'll get this body is bent and we'll get the new layer as well as new section A dash, B dash, C dash, D dash, and as well as we'll get the new layer is E dash and F dash. Okay, and neutral axis is a N dash, A dash. When you extend this two section A dash, B dash and C dash and D dash, this will be made at a center point O. This will be made at a center point O, and C will get the radius of curvature from this center point to the top of the object. Okay, this is the radius of curvature. It is denoted by the R, and we get the small angle. This small angle in between A dash, O dash to this at the center. Okay, this angle, this is denoted by the theta. Theta is known as a subtended angle. Okay, remember you have to you will get after solving or you are finding the stress after the loading on the given component, then you will get that bending formula, or we can say the bending equation. M by I is equal to sigma by y is equal to E by R. Again, what is the M? What is the M? M is the bending moment. Bending moment. Already we have seen what is the bending moment in the unit number 2. This is given in Newton meter, or we can say the Newton mm. Means how to calculate that bending moment? This is the moment is nothing but the force into distance. When you apply any force on the given component, that into the distance. Okay, this is the bending moment. This is in Newton mm. What is the I? I is the moment of inertia. Last lecture we have seen moment of inertia. How to calculate that value of I? You know, there are different sections. You have one, suppose rectangular section is given, circular section is given. You will get the different I value for the each section. Moment of inertia, this is given in Newton, this is given in mm raised to 4 or meter raised to 4. Remember that I value, you will get the moment of inertia always in mm raised to 4 or meter raised to 4. Then sigma is the bending stress. Bending stress. Some books it is denoted by F suffix C. Okay, flexural stress. F suffix C. Don't confuse. You know the stress unit Newton per mm square or meter square. Then Y. What is the Y? See, here I have shown the Y from the neutral axis to the near distance. Okay, you have to check the outermost value of that Y from the neutral axis. Suppose, for example, we will take the rectangular body. What is the value of the Y? Where is the centroid? At the centroid is at the center. Suppose this is the D. This is the D and this is the B. B and D. Okay, width and depth. D is there. What is the half distance? Where is the centroid? D by 2. Where is the outermost layer from the neutral axis? This is the neutral axis, right? And is the neutral axis. This is the outermost value of the Y. Okay, this is Y is equal to again D by 2. At the bottom or at the top, you will get here same value because of the symmetric part or rectangular body. We have taken the symmetric means you will get the same image above the neutral axis and below the neutral axis. If we have taken the section at the neutral axis. Okay, all of you getting what is the Y? Y is the stress at distance Y from the neutral axis. This is the outermost distance from neutral axis. Remember that. Outermost distance from the neutral axis. If you have given the hollow rectangular part, then which is the outermost distance? Yes. If you have given suppose hollow rectangular part, here is a one more rectangular is given. And which is the Y distance? You have to consider the outermost. Which is one outermost? This one. Then suppose here is a capital D by 2 is there. I will explain in the section modulus. Remember that. Okay. Y. All of you getting what is the Y? Y is the outermost distance from the neutral axis. And what is the unit of that? This is given in mm or meter. What is the E? E is the angle modulus. You know that. Angle modulus, it is also called as a modulus of elasticity. This is given for the material. Okay. It is given in Newton per mm square. And R is the radius of curvature. This is also given in mm. This R is given radius of curvature. This is the bending formula. You have to remember with the help of meaning. Okay. If you remember this formula, then easily you can solve the given numericals. Okay, I want you getting what is the bending formula? M by I is equal to sigma by Y is equal to E by R. Then there is some assumptions are given. Okay, remember that. Assumptions, which assumptions are we want to consider before going on the theory of that simple bending? We know there is some assumptions made for the theory of simple bending. Okay, theory of simple bending with their assumptions. Okay, you have to remember some assumptions. The material of the beam is homogeneous and isotropic. First assumption, the material of the beam is homogeneous and isotropic. What is the you will get the throughout same material properties. Okay, you will get the same material throughout. For example, wood. Okay, wood is the homogeneous material. And what is the isotropic? You will get the same what we can say, the elastic property of that material. You will get same in all directions. Okay, if you are checking in x direction, y direction, z direction or any other direction, then you will get the same elastic property of that in all direction in the isotropic material. Remember the meaning, homogeneous and isotropic. The material of the beam, it should be homogeneous and isotropic. This is the first assumption. Then what is the second assumption? The value of E means what? Young's modulus, or we can say the modulus of elasticity is same. Okay, this value is same in compression as well as in tension. Okay, there will get, when you apply some load on the given component, then we will get the compression above the neutral axis or below the neutral axis, we will get the tension. In that, this E value is the same. In the compression and tension. This value will not change. Okay. Then third is in the transverse loading. In the transverse loading, or we can say the section, the body is plane. Before and after loading. Okay, in the transverse loading, or we can say the transverse section. Okay, the body is plane before loading and also after loading. This will be same. You will get the plane body after loading and before loading. And fourth is each layer of the body free to expand and contract. Okay, remember that fourth assumption. Each layer of the body is free to expand, also contract. Okay, remember that some assumptions you have to consider in the theory of simple bending. Okay, all of you getting? Then next part is the section modulus. Okay, this is the important part. When you are solving the numerical, then you know how to calculate the section modulus. Okay, lastly, also I have given little bit idea to you. Okay, section modulus. What is meant by section modulus? Section modulus is nothing but it is the ratio of moment of inertia to outermost distance from the centroid. Okay, sectional modulus is nothing but Z is equal to I divided by Y max. It is the ratio of moment of inertia. I means what? Moment of inertia of the given body about the neutral axis to the outermost distance from the neutral axis. It is called as a section modulus and it is denoted by the Z. What is the unit of I? I is given in mm raised to 4. What is the unit of Y max? Mm is there. And so what is the unit of Z? mm cube is there. Or meter cube is there. Remember the units are very important. Then we know the bending formula. M by I is equal to sigma by Y. When we will get the maximum stress induced in the given member, if the Y value will be maximum, then we can write the equation sigma max is equal to m by I is equal into y max right, and m is equal to, also we can write, see, m is equal to I divided by y max into sigma max. Again, what is the I divided by y max? See, as per the definition, we can write the z. M is equal to z into the mx. Then m is nothing but the moment of resistance. Okay, this m is z. Check that, z into sigma max. Okay, this z is represent the strength of that section, or we can say the strength of the section. Okay, z is represent the strength of the section. You can calculate the moment of resistance here, also the bending stress, maximum bending stress induced in the given component. Then this z is represent the strength of the section. Okay, strength of the section. Then how to calculate the sectional modulus for the different section? Okay, how to calculate the, first we will take the rectangular section. Okay, remember that rectangular section. Okay, you know the represent the rectangular section having the two dimensions. One is the b width and second is a d is the rectangular section. Then we want to calculate the value of z. We know z is equal to what? I by y max. Okay. And how to calculate the moment of inertia? You know the moment of inertia I for the rectangular section, b into d cube divided by 12. b d cube divided by 12. Okay. And what is the y max value? Where is the neutral axis? At the center. NA, neutral axis. And what is this distance? Outermost distance from the centroid, at the top or bottom. Then you will get the y max is equal to d by 2. Then if y max is equal to d by 2. Once you have got the two value, then easily you can calculate the value of z. Z is equal to bd cube divided by 12, d divided by 2. Then again check that, you will get, what you will get, bd square by 6 is there, na? bd square by 6. This is the value of z. If you have taken, then again see, if you have taken the hollow rectangular section, this is the bd cube divided by 6 for the, this one, z is equal to bd cube divided by bd square by 6 is there. Then second one is the hollow rectangular section. Hollow rectangular section. Okay. If you have considered the hollow rectangular section, then what is the value of section modulus? Check that. Okay. For this outer rectangular, we will consider the capital B is the width, and depth of that rectangular section outer side, capital B is there, and inside we will consider the depth small d and width is a small b. Then how to calculate the sectional modulus? What is the I value for the hollow section, hollow rectangular section? Yes, anybody? I is equal to what? bd cube divided by 12 minus, we move on to the minus this hollow one, inside one. Okay, small bd cube divided by 12 is there. And what is the y max value? What is the y max? You have to check the outermost distance from the neutral axis. Don't consider the inside one. you have to consider the outermost. Which is the outermost? This one, capital one. Okay, this is the y max. You can take at the bottom or at the top. Okay, here is a symmetric. That's why you will get the same d by 2. If you have taken the bottom from the neutral axis, again you will get the capital D by 2 is there. Capital D by 2 is there. Then what we will get? Change that Z is equal to this BD cube divided by 12 minus BD cube divided by 12 divided by D by 2. D by 2. What you will take the common? You can take the common 1 by 12 is there. 1 by 12 is there. 1 by 12 and this 2 means you will get the 6. 1 by 6. BD cube. When you solve this, then you will get the BD cube divided by 6 is there. Check that. D6 is there, no? 6D. D as it is. D as it is. You will get this Z. Okay. In this way, we want to calculate the value of Z. Means you will get nothing but from the bending formula MYI is equal to sigma by y. You will get the two value I and y with the help of section modulus. Similar way, you can calculate the value for the circular section. Okay, we'll check that circular section. Yes, what is the value of I for the circular section? Anybody? Do you know the I value? We'll take third one, circular section. Circular section. What is the value of I? We consider circular section having only one dimension is a d. Right? This is the diameter of given circular section d. What is the value of I? I is equal to pi by 64 into d square. Okay, we will consider the small d. D raised to 4, pi by 64 into d raised to 4 is there, not square. Okay, check that. Y max is equal to, what is the y max? You have to take the neutral axis. Where is the neutral axis? At the center. Okay, you have to check the outermost distance. Outermost distance, which is the outermost distance? This one or this one? You can take at the top or at the bottom. Again this one d by 2. D by 2 is there. Right? Then you will get the Z is equal to pi by 64 into d raised to 4 divided by d by 2 is there. D get cancelled and you will get the pi by 32 into d cube. Right? Z is equal to. This is the sectional modulus for the circular section. Similar way, if you have given the hollow circular section, then how to calculate the section modulus? Check that. I will draw here hollow circular section. This is the hollow circular section. Here you will get the two dimension. Which two dimension? Outer side we will consider the capital D. Okay. Outer side we will consider the capital D, and inner side we will consider the small d. This is the dimension. Then what is the value of I? Okay, we know the formula for the solid. I is equal to pi by 64 into d raised to 4 minus, you have to minus that hollow one inside one, pi by 64 into small d raised to 4. And what is the y max? Again, how to calculate the y max? You have to consider the outermost part from the centroid or neutral axis. You will get again capital D by 2. Then you will get the Z is equal to, you take the common outside, pi by 64 is the common, then d raised to 4 minus small d raised to 4 divided by b by 2, d by 2. Again you will get the pi by 32d na, pi into capital D raised to 4 minus small d raised to 4 divided by 32d is there. 32d is there. Okay, check that. You will get. In this way, you have to calculate for the triangular section, for the rectangular section or circular section, hollow section. Okay, each and every section, or if you have given the suppose T section, then again there you will get the rectangular, right? If you have given the rectangular section and inside that you have given the circular hole, again you will get the both for the circular section and rectangular section. If you have given the square, okay, if you have given the right angle isosceles triangle, then you have to calculate the sectional modulus for that. Okay, all of you getting? This is the theory given in the third unit. Okay, next lecture we will see the numericals on the third unit. Okay, today we will stop.